My name is Barry Rawlins, and I'm a soil scientist working at the British Geological Survey near Nottingham. This presentation shows the main findings of the work I have done to address a specific question. Are farmers' data sufficiently robust for monitoring topsoil indicators at national scale? This work has been done on behalf of the Natural Environment Research Council under an innovation internship working with colleagues at DEFRA. I have worked with other colleagues named on this slide, both from BGS and Rothamsted Research. The data for this project were supplied by NRM Laboratories, specifically my colleague in this project, Sean Stevenson.
Regulatory authorities, such as government departments, need to understand how soil properties change through time to understand how soil functions may be changing, but also to understand the impact of or need for specific soil policies. In the UK, a set of 13 topsoil indicator properties have been identified as a priority for soil monitoring. In this project, we consider whether 5 of these soil indicators could be monitored using farmers' data across agricultural land of England and Wales, about 82% of the land surface. By farmers' data, we mean measurements made on soil samples on behalf of and paid for by farmers across all of England and Wales. The soil material is generally submitted to commercial laboratories by professional agronomists. Farmers and agronomists may direct their sampling of soils on their farm to particular issues they are aware of. Their approach is purposive, and this may have implications for the soil measurements. Specifically, measurements on these soil samples may, on average, be different to samples which had been collected randomly or without purpose. This difference or bias is important because it could give us a misleading understanding of the soil indicators. Soil measurements made on soil samples from farmers' soil also need to be analysed using a specific statistical approach called a model-based analysis, and that is what we have done in our study. Surveys undertaken by research organisations are typically based on a randomised sampling approach, and the analysis of these data is generally simpler than a model-based approach. We can compute simple mean or average values and the associated confidence intervals for them for particular land use types at national scale. We refer to this as having a design-based inference. By contrast, for farmers' data, we must use our model-based approach to estimate mean values and confidence intervals of a particular soil indicator. We do this by developing a spatial model of the soil measurements, which means we need to know the grid coordinates from which the soil was collected, or the coordinates of the farm. We can then compute a mean value and confidence interval for a particular land use and indicator over either England or Wales based on the extent of this land use from a land cover map. In this study, we focus on 2 land uses, arable and horticultural land, or improved grassland. In addition to the different sampling approaches, there are other potential sources of bias between the farmers' data and surveys by research organisations. These include the timing of sampling, the different analytical methods that may be used to measure soil indicators in the laboratory, the depth range over which soil samples are collected, which may be different for the various survey approaches. In this study, we used farmers' data from NRM laboratories spanning 12 years. In the database, if the farm did not have a postcode, we used a geocoding tool to retrieve the postcode using both the farmer's name, the name of the farm, and local town details. Our final dataset had more than 20,000 soil measurements by farm and year. For each farm, we calculated the median value of each topsoil indicator for each year. This provided us with sufficient data to assess all the 5 indicators, with the exception in one case of organic matter. To assess changes over time within the farmers' data, we split the measurements into 2 periods, 2004-2009 and 2010 to 2015. Here we show maps of soil pH across England and Wales for these 2 periods, excluding areas which are not arable or improved grassland. Note the large areas with soil pH less than 6 in northern England and Wales in the years 2010 to 15 compared to that in 2004 to 2009. The aims of our study were to compare 5 topsoil indicators across England and Wales for both farmers' data and other national scale surveys to assess whether the farmers' data may be useful for national scale monitoring. We compared the mean estimated values of the indicators from the farmers' data for the 2 land use types across England and Wales with those from the other surveys. Here, CS stands for Countryside Survey, with sampling from 2007, the European Lucas Survey from 2009, the resampling of the National Soil Inventory in 2003, and the Representative Soil Sampling Scheme from 2001. We try to identify reasons for significant differences between the farmers' data and other surveys. We also determine the size of change in indicators between the 2 periods of the farmers' data. Our first indicator is topsoil pH. The figures in bold are the mean pH values for the different surveys for the 3 land use and nation combinations. Note how similar the mean values are for the farmers' data 2004 to 9 and 2010 to 15, and the Lucas survey, which have exactly the same analytical method. The CS 2007 survey determines pH on field moist samples, which may account for the slightly larger overall values. The confidence interval estimates around the mean are smaller for the farmers' data because there are many more samples. See the row denoted N or N farms in the table. The box plot shows the year-to-year variation in soil pH in the farmers' data for arable soils of England, with the horizontal line showing the mean estimates from the model-based analysis. The lower pH values in 2010 may be due to a shift in the geographic distribution of the samples. In 2010, more samples were analysed from the north and west of the study region, where the soils are generally more acidic with lower pH values. Comparison of the available phosphorus or Olsen P mean values for the surveys is complicated. First, note the similarities between grassland in England and Wales between the farmers' data and CS 2007. But there is a large difference when we compare the mean estimate of arable soils for England for the farmers' data with Lucas and CS 2007. Part of this difference is due to the differences in the analytical method, as we will see in the next slide. Note the similarity between the farmers' data mean values for both time periods and that from the representative soil sampling scheme, which shows an average value for all 3 land use and nation combinations. The representative soil sampling scheme has the same analytical method as the farmers' data. This is a scatter plot of 2 sets of measurements on the same soil samples with a range of available phosphorus concentrations. In the data plotted on the x-axis, no charcoal was added to the extracting solution, whilst in the method used for data on the y-axis, activated charcoal was added. You can see that concentrations on the y-axis are systematically larger than on the x-axis. They're above the 1-to-1 line. There are other small differences between the 2 methods, but we think the activated carbon or charcoal is having a significant effect. Note the regression line has a slope of 1.32, which means on average the Olsen P concentration in samples with activated charcoal are 32% larger than those without the charcoal. This could account for some of the differences we observe between the smaller estimated mean values of the farmers' data compared to the Lucas and CS 2007 surveys, the latter which have charcoal added to the extractant. The Lucas survey has larger mean available potassium concentrations compared to the farmers' data, which we consider is due to the different extractant used, ammonium acetate in the former and ammonium nitrate in the latter. The mean value for the representative soil sampling scheme is similar to the arable soil values for England in the farmers' data, whilst the farmers' data have lower estimated mean values for grassland compared to the representative soil sampling scheme. The resampling of the National Soil Inventory from 2003 had larger available magnesium concentrations than the farmers' data for the England land cover types, and a similar value for Welsh grassland. The overall mean value for the representative soil sampling scheme from 2001 is similar to the farmers' data for English arable soils, but smaller concentrations are observed than for the two sets of grassland estimates in the farmers' data. There were only sufficient organic matter data to estimate mean farmers' data values for the 2010 to 15 period across the two land cover classes for England. These farmers' data values are smaller than those reported by CS 2007, but their two confidence intervals do overlap. Note that they both use loss on ignition to estimate organic matter content, whilst the Lucas survey adopts an elemental or combustion-based carbon analysis, and we converted these measurements to organic matter contents. And this different analytical method may account for the larger observed values we see for all land use types for the Lucas survey. Here we provide the overall change in farmers' data for 4 topsoil indicator values and show whether this change was statistically significant for arable soils of England. Only the 0.04 unit reduction in topsoil pH was statistically significant. Here we summarize the main findings for topsoil pH. The fact that the farmers' data and Lucas survey mean estimates are very similar is very encouraging. The maps of soil pH, see slide 6, show large areas of grassland soil in northwest England and Wales which have pH values less than 6. The recommendation in the fertilizer manual from DEFRA called RB209 is that topsoil pH should be above 6 for optimal yield, and this may be important for farmers in these areas. We showed there was a systematic bias between the analytical methods used in the farmers' data and the national scale surveys that accounted for some of the observed differences between mean values. But we cannot exclude the possibility that sampling may also contribute to some of the observed differences. What is noteworthy is that farmers will typically have smaller values of available phosphorus reported to them by the NRM laboratory than would be the case if these samples were analysed by a laboratory in which charcoal is added in the extraction step. This has implications for how much phosphorus fertilizer farmers will choose to add to their fields, in relation to the guidance provided by DEFRA in their fertilizer manual. For available potassium, the farmers' data are more similar to the representative soil sampling scheme mean values from 2001 because it has the same extractant in the laboratory method, whilst the Lucas survey concentrations are quite different because it uses a different extractant. We could not explain why the available magnesium concentrations from the National Soil Inventory resampling are larger than those from the farmers' data for soils across England. The representative soil sampling scheme mean values from 2001 are generally similar to those from the farmers' data. Here we summarize the main findings relating to the organic matter concentrations. We need more farmers' data in the future to make reasonable estimates, but there is considerably more farmers' data for organic matter in the second period compared to the first, which suggests that more organic matter analyses are being requested in the last few years of our study, that is between 2010 and 2015. Our main findings are that first, there is reasonable agreement between estimated mean values of topsoil indicators across national and land cover combinations for farmers' data and representative national scale surveys. Second, we consider that farmers' data offers a potential means of monitoring these soil indicators at national scale that complements but does not replace monitoring using statistically designed surveys. We provide some suggestions here on how farmers' data might be improved. In particular, if farmers and agronomists could ensure GPS coordinates are recorded for each field from which they collect a soil sample, using a smartphone for example, and this information is included with the sample, we would have much more data to work with. Also, it is very important that the land use in the field is recorded, and it would also be helpful to know if this field was sampled for a particular reason. If you have any questions about this work, you can contact me at my email address shown on each slide. Thanks for watching.